Welcome to Elementary Functions. Today we're going to talk about complex numbers and polar coordinates. My name is Wendy Fresh. I'm from Portland Community College, and this is Math 112. The objectives for this lesson are to define a complex number, to convert between rectangular and polar forms, and to use Euler's formula to find an nth root of a complex number algebraically. Let's first begin by defining what a complex number is. Complex numbers are numbers of the form z equals x plus y I, where x and y are real numbers. The real number x is called the real part of the number. The real number y is called the imaginary part of the number. That's because the y is connected with the I, which is the imaginary piece. In addition, I to the second power is equal to -1. So let's make sure we know what type of axes we're looking at. Example 1, a complex number z equals x plus yi can be seen geometrically as the point x, y in the xy plane. Label the figure to show that in the complex plane, the horizontal axis is called the real axis. So this is the horizontal. I'm going to call that the real axis. And the vertical axis is called the imaginary axis. Example 2. Draw your own complex plane to plot the following complex numbers. Before I draw that complex plane, let me just identify parts of these complex numbers. In z equals 3 minus 2i, the real portion is the number that doesn't have an I on it, so that would be 3. And the imaginary portion is the part that does have an I on it, so that would be -2. For z equals 2 plus 5i, the real portion is 2, and the imaginary portion is 5. In z equals 3i, the real portion is 0, and the imaginary portion is 3. And in z equals -4, the real portion is -4, and there is no I in this one, and so the imaginary part is 0. To draw my own complex plane, if you recall from the last slide, it doesn't look a whole lot different. The only difference is what I call each one of these axes. The horizontal axis is my real axis. So that's where we're going to see all the real portions of these numbers. And then the vertical axis is my imaginary axis. And that's where we're going to see all the imaginary parts of the number. So for z equals 3 minus 2i, starting at the origin, first of all, actually, let me put some tick marks on here. 1, 2, 3, 4, 5, and -1, 2, 3, 4, and 5. And how about 1, 2, 3, 4, 5 on the imaginary axis, and -1, -2, -3, 4, and -5 on the imaginary axis. All right, so for z equals 3 minus 2i, starting at the origin, the real portion is 3 units, so I'm going to move to the right on the real axis, and then I'm going to go down 2 on the imaginary axis to put me at about right here. That's in my fourth quadrant. Z equals 2 plus 5i. Starting at the origin, I'll move to the right 2, and I'll move up 5. So that keeps me in the first quadrant. For z equals 3i, the real portion is 0, so I'll move nowhere on the real axis, but on the imaginary axis, I'll go up 3. So that puts me right on what we used to call the y-axis. And then for z equals -4, the real portion is -4, so I'll go to the left 4, and the imaginary portion is 0, so I'm just going to be sitting on the real axis. A polar representation of the complex number z equals 3 minus 2i can be written by finding the angle theta and the radius of the circle drawn to the point z equals 3 minus 2i. The radius is called the magnitude, and it's denoted with a z and vertical bars around it. Use what is known about finding angles from an initial side to a terminal side and right triangles and their hypotenuse to find theta and the magnitude of z. Now remember, the magnitude of z is what we know as the radius. So if I connect from the origin to that point 3 minus 2i that was in blue, I believe that I can identify from what we've done before, I can identify a right triangle where the hypotenuse is what I'm trying to find. This seems to have legs that are 3, so I'm going to say 3 squared plus negative 2 squared, and that's going to give me r squared. So I'm using the Pythagorean theorem to find r squared. R is going to be the square root of 13, and so I'm going to say that z is equal to the square root of 13. To find theta, I'm going to use probably my SOHCAHTOA rules. Let me just pull that triangle out and make it a little bit larger. What we have is something that looks like this, and what I know is that I was given that the horizontal length is 3, that the vertical length is negative 2, and that I have a radius of the square root of 13, and I want to find theta. Now the square root of 13 was not given, so I'm going to use the 3 and the negative 2 that were given. My right triangle is in that upper right corner, and so the sides that have been given to me are opposite and adjacent. So I will use tangent and say that the tangent of theta is equal to the side opposite of theta, which is negative 2, divided by the side adjacent. So in my calculator, I'm going to put tangent inverse of negative 2/3. And depending on whether you are in radians or degrees, I am in radians, my answer comes out. I'm going to expect that that answer is either a very large angle, or because I'm moving, it looks like in this little small piece, I'm going to expect a number that's negative. And when I put that in, I get negative 0.588. And just to remind myself, I'm going to go ahead and write radians on this. So now let's take a look at converting between rectangular and polar forms. A complex number can be written as z equals x plus yi. A polar coordinate includes r and theta. From previous lessons, we know that the relationship between x, y, r, and theta is that x is equal to r times the cosine of theta, and that y is equal to r times the sine of theta. Therefore, by substitution, if r is greater than or equal to 0, and theta is between 0 and 2 pi, then the complex number z equals x plus yi can be rewritten in trigonometric form as z equals, instead of x, I'm going to substitute in what I said that x is equal to, which is r cosine theta. So I'm going to write r cosine theta. And in the place of the y, I'm going to substitute what I said that y is equal to, which is r sine of theta. And I'm going to be careful to keep that I separate from the inside of the sine of theta. I can either put parentheses around it like you just saw me do, or I can move it to the front, which I think I'm going to end up doing. Now both of these terms have an r in it, so it might be nice to factor that r out. And if I do that, I'm left with cosine theta plus, let me move that I to the front and say I times the sine of theta, where the magnitude is equal to the radius. So let's take a look at an example. We are being given the rectangular form of a complex number. Rectangular because we are being given x and we are being given y. To turn this into a trig form of a complex number, we need to know what r is, and we need to know what theta is. Now, I purposefully picked this first one because we already did this one on the previous slide. We came up with a radius of the square root of 13. So I'm going to say z is equal to the square root of 13 times the cosine of theta. Now, what was my theta? My theta from the previous slide was negative 0.588. And the reason you're not seeing me write that down is because negative 0.588 as an angle is not between 0 and 2 pi. So I need to rewrite it. Theta is equal to negative 0.588, but because of the period of the sine and the cosine curve, I know that if I add 2 pi to it, that will get me an angle that is equivalent to my theta. Now, if I take negative 0.588 and I add 2 pi to it, I get 5.69. So 5.69 is what I'm going to use, and I'm going to have that I on the outside. And I get something like that. Now, I know I could take this further, but if I did take it further, it would just take me back to the rectangular form. There's a reason why I'm going through this process, and that's coming up in just a little bit. Now, the opposite of converting from rectangular to trig is converting from trig to rectangular. So, in this particular example, I'm being given a radius of 2, and I've got a theta of 2 pi. Now, technically speaking, I should rewrite that theta of 2 pi because up in my definition, let me circle it again in red, theta needs to be between 0 and 2 pi, not including 2 pi, but including 0. So I think that I will rewrite 2 pi, how about as just 0. So I know r and I know theta, and what I need to find out is x and y. Now, what is the relationship between x, y, r, and theta? Well, it's on this slide. We know that x is equal to r cosine theta. We know that y is equal to r sine of theta. So let me just work this off to the side. X is going to equal what my r value is, which is 2, times the cosine of 0. And the cosine of 0, that should be a 0, not a theta. The cosine of 0 is 1, and 2 times 1 is 2. And for my y value, 2 times the sine of 0 is 0, and so I get a y value of 0. So in rectangular form, z equals 2 times the cosine of 2 pi plus I times the sine of 2 pi turns into z equals 2 plus 0i, which I'm going to say is just 2. When you end up getting rid of all of the imaginary parts of a complex number, we say that that complex number is purely real. Now, we went through the process of actually solving for x and y, but I want you to think about the unit circle. Let me just draw this off to the side, and I'm going to run out of room, but let me just make this small enough so that you can see it. If you imagine on this one where a theta of 2 pi or 0 is, we know that we are on the positive x-axis. And if we have a radius of 2, that puts us 2 tick marks out on that axis. If I put a point there, is it any surprise that my x came back as 2 and my y came back as 0? I would say no. When we have a point that is purely real, in other words, it lies right on the axis, or purely imaginary, lies right on an axis, we can really just take a look at the circle where it would be on a circle and come up with that x and y. Now for the next one, it's going to be a little bit more work. In this one, with a cosine and a sine of 2 pi over 3, we know that we're not sitting right on one of the axes. My radius is still 2, but my theta is 2 pi over 3. Pause the video for a second and see if you can determine what is x and what is y. All right, now that you're back, x is going to equal, what did we say, r cosine theta, so 2 times the cosine of 2 pi over 3. And let's see, that's going to be 2 times, the cosine of 2 pi over 3 is negative 1/2, and so I get negative 1. And my y value is going to be 2 times the sine of 2 pi over 3. So that's 2 times root 3 over 2, and so I get root 3. So in rectangular form, I end up with z equals my x value, which is negative 1, plus my y value, which is root 3, and with an I hooked on. In the 18th century, the Swiss mathematician Leonhard Euler made a connection between exponential functions and the sine and cosine functions involving complex numbers. And this is Euler's formula. It says e to the I theta is equal to the cosine of theta plus I times the sine of theta. And the e that we're talking about is the e that you've probably seen in previous math classes, approximately 2.7. This allows us to take the definition from the previous page and rewrite it to show the progression of a complex number in rectangular form to trigonometric form and finally to polar form. So here we go. We start out with z equals x plus yi, and z equals x plus yi, we said, is the rectangular form. This is the rectangular form of a complex number. And then on the previous slide, we took the fact that x is r cosine theta and y is r sine of theta, and we substituted those in and we factored out an r, and we said, okay, now we have the trigonometric form. Now, Euler's formula tells us that e to the I theta is equal to the cosine of theta plus I times the sine of theta. And if you look right here, what I just said out loud about Euler's formula is written in my trigonometric form. So in the place of cosine theta plus I times the sine of theta, I'm going to substitute in e to the I theta. And once I multiply that by r, I end up with what I'm going to call the polar form of a complex number. So let's take a look at an example. Use Euler's formula to extend the table from example 3. Example 3 had the rectangular form, which we then changed into the trig form. Go ahead and pause the video for a second and rewrite your values for row 1, 2, and 3, column 1 and column 2. All right, now that you're back, let's see if you agree with me. For the trig form of z equals 3 minus 2i, I got z equals the square root of 13 times the cosine, I think I said, of 5.69 plus I times the sine of 5.69. Now before I go on to row 2 and 3, let's just move over to the polar form. The polar form simply says that z is equal to whatever my radius was, so in this case the square root of 13, times e to the I theta. Well, my I value was 5.69, So I'm going to raise this to the 5.69 I power, and that is it. For row 2, we saw the radius of 2, and of course we changed this to a 0. And so in rectangular form, that gave me z equals, I think, what did we say on this one? Z equals 2 plus 0I, or just z equals 2. In polar form, this would be z equals my radius and e to the I theta, so 0I. For the third row, I came up with z equals -1 plus the square root of 3I. And in polar form, I'm going to have that radius of 2 raised e to the 2 pi over 3I. And then finally on the last row, I give you the polar form and I ask you to write that in complex numbers. So knowing that in the polar form I have 3 times e to the I times pi over 2 tells me that the radius is 3 and that the theta is pi over 2. So substituting that into the trig form of a complex number, I get 3 times the cosine of pi over 2 plus I times the sine of pi over 2. And what does that equal? What is 3 times the cosine of pi over 2? Cosine of pi over 2 is 0, and 0 times 3 is 0, plus, what is the sine of pi over 2? It's 1, and 1 times 3 is 3. And so I get 3I. Now, we saw earlier on the second row that we called z equals 2 purely real. On the fourth row, we're going to call this one purely imaginary. Now let's look at another objective. Use Euler's formula to find an nth root of a complex number algebraically. So you might be thinking, why are we doing this? In other words, what do you think is the purpose of writing a complex number in polar form? In other words, consider if you were asked to find a root of z. If the complex number is in rectangular form and you were asked to find the root of it, let me just remind you that in rectangular form, if I said what is the square root, for example, z is equal to x plus yi, and you would be taking the square root of this sum. That's about all that you could do with it, because what we know is that this is not true. It is not true that the square root of a sum is equal to the square root of part of that sum plus the square root of the second part of that sum. For the trig form, that was also a sum. We pulled out an r and we were left with cosine theta plus I times the sine of theta. So if I try to square root, although I do have a product with the r, I don't have a product with the cosine theta plus I sine of theta, so I wouldn't be able to do much more. The polar form is the only one where we see a product. And so if I was asked to find a root and square root this, what I could say is that this is equal to the square root of r times the square root of e to the I theta. So in other words, the purpose of doing this is so that we can simplify it down a little bit more. So let's take a look at an example. find a square root. Notice it says a square root because we know that if you're being asked to find a square root, you can have the positive or the negative. So there's two possible square roots. We're only being asked to find one of those. Also recall that another way of writing a square root, having that radical symbol, for example, if I said the square root of 4, another way of writing a square root is by writing 4 to a power of 1/2. So if I ask you to find a square root of the square root of 3 plus I, another way of saying that is to find the square root of 3 plus I, all raised to the 1/2 power. So as we just mentioned, in order to be able to take a root of something, it's helpful to have it written as a product. So what our goal should be on this problem is to take this sum of the square root of 3 plus I and rewrite it as a product. Now, square root of 3 plus I is currently in rectangular form. It's like saying z equals the square root of 3 plus I, where my x value is the square root of 3 and my y value is 1. The other thing that I think may be helpful for you to note is that if you were to graph this complex number, in other words, starting at the origin, if you move on the real axis, square root of 3 units, and you move on the imaginary axis, 1 unit, you would end up in quadrant 1. All right, so to get this into polar form using Euler's formula, you need to find r and you need to find theta. So if you know x and you know y, can you find r and can you find theta? Using the Pythagorean theorem, we can say that x to the second plus y to the second is equal to r to the second. And my x value is root 3, and my y value is 1. So I get 3 plus 1 is equal to r squared. It looks like r is going to be 2. For theta, the only thing that I know for sure that was given to me are the x and the y. Now I know that I just found the radius, so technically speaking, to find theta, we could use SOHCAHTOA rules for sine, cosine, or tangent. Because x and y were given to me, I'm going to go with the tangent. And I'm going to say that the tangent of theta is equal to my y value over my x value, so 1 over root 3. And if I do tangent inverse of this, I get a theta that is equal to pi over 6. And that actually makes me happy because pi over 6 is in the first quadrant like I thought it should be. All right, so first step, find r and find theta. Second step, now let me write this in polar form. So polar form is going to take this and write it in the form z equals r times e to the I theta. So my r value is 2 and my theta is pi over 6. Now that's what z equals. And notice that right from the get-go, I let the original problem be called z. So if I want to find a square root of z, then what I need to do is to take and raise this z to the 1/2 power on the left, and then do the same thing on the right. So how do you take something and raise it to a power? Well, this is the same thing as writing 2 to the 1/2 times e to the pi over 6 times 1 over half. In other words, how do you take a power to a power? And the answer is that you multiply those exponents. So I end up with 2 to the 1/2 times e to the, what is pi over 6 times 1/2? The answer to that is pi over 12. And I can see in my original work, let me fix this, I forgot an I. I'm going to pop an I in there right now. And so I get that the square root, or a root, of the square root of 3 plus I is equal to 2 to the 1/2 power times e to the pi over 12 to the I power. Now that's a great answer. However, my third step is that if I started with something in rectangular form, I should end with something in rectangular form. In other words, I only put it into polar form so that I could easily find a square root. What I'm going to do at this point is use the new r that I have and the new theta that I have and the fact that x is equal to r cosine theta and y is equal to r sine of theta, and that z is equal to x plus yi, and I'm going to rewrite this root in terms of rectangular form. So what is x? X is going to be equal to whatever my r value is, which is 2 to the 1/2 power times the cosine of pi over 12, let me put parentheses around that, plus I times the sine of pi over 12. Now before I go any further, I think what I'll do is I'll grab my calculator and I'll actually try and compute what is 2 to the 1/2 power times the cosine of pi over 12. That is my x value. And a decimal approximation is okay here. I get 1.366 plus, let me take that 2 to the 1/2 power and multiply it by the sine of pi over 12, and I get 0.366 with an I hooked on. Now believe it or not, if you put into your graphing device or your calculator the square root of the square root of 3 plus I, your calculator is going to produce this same result. And if you think about it, that result is also in quadrant 1. Now this was an example where we found a square root. There is another square root, and that's what we're going to look at on the next slide. Example 6. Find the two square roots of -1 plus I times the square root of 3. So we're looking for both roots this time. And before we go too far into this, what I like to do is make sure that I know where that complex number is. If I were to graph -1 plus I times the square root of 3, I would go to the left 1 unit on the real axis, and then I would go up square root of 3 units. So I am in quadrant 2. I want to remember that. The other thing I want to make note of is that my x value is -1 and that my y value is the square root of 3. And that in order to find the two square roots, I need to get this rectangular form into polar form. And in order to get it into polar form, I need to find r and I need to find theta. So what's my r value? Well, x to the second plus y to the second is equal to r to the second. So -1 squared plus root 3 squared is equal to r squared. So 3 plus 1 is 4. It looks like I have a radius of 2. Now, how about theta? So here's what I can say. I can say that the tangent of theta is equal to my y value over my x value, or if I feel pretty confident about my radius, I can say that the sine of theta is equal to my y value over my radius, or I can say that the cosine of theta is my x value over my radius. Now, remembering that I'm in quadrant 2, pick the one of these that you think is the easiest for you to figure out and puts you in the right quadrant. So I would say probably if you try to use a calculator, your calculator is going to give you an answer for the tangent in quadrant 4. If you're okay with adding the period of pi to this to get you into quadrant 2, then that one's a fine one to use. Sine of theta is going to put you in quadrant 1 with your calculator. If you're okay with taking 180 degrees or pi and subtracting out that angle to get you into quadrant 2, then that's a fine one to use. It looks like cosine is the only one that is going to give me an answer in my calculator that would put me into quadrant 2. So what I'm seeing here is that theta, this is going to put me in quadrant 2, theta is the angle that produces a cosine of -1/2, and that angle is 2 pi over 3. In order to find the 2 square roots, we need another way of writing 2 pi over 3. If you're being asked to find 3 cubed roots, you would need 3 ways to write that angle. I'm being asked to find 2 square roots. I've got 1 theta, another way of writing theta, and it can be anything that you want. I can add 2 pi, take away 2 pi, but I have to make sure that I'm in the second quadrant. I'm going to go ahead and take that 2 pi over 3 and I'm going to subtract 2 pi. Now that's the same thing as subtracting 6 pi over 3, which is going to give me -4 pi over 3. So those are the 2 thetas that I'm going to use for my theta. All right, now I'm possibly going to run out of room, so let me just put a border here. Now my job is to actually take the root. So I started out as z equals -1 plus I times the square root of 3. If I want to take that to the 1/2 power, it's going to look something like this. I'm going to take the square root or raise it to the 1/2 power. Now z to the 1/2 power, I'm going to rewrite the rectangular form in r times e to the I theta. So my r, remember, was 2 and e to the I theta. Well, one of my thetas was 2 pi over 3 to the I, so I'm going to raise that to the 1/2 power. Or to get the other root, I'm going to take 2e to the -4 pi over 3i to the 1/2 power. I'm going to work both of these out, and believe it or not, they're going to give me different answers. Those different answers will be the 2 roots of this complex number. All right, so let's take a look at the first one. I'm going to take 2 to the 1/2 power, and I'm going to take e to the 2 pi over 3 I to the 1/2 power. The 2's will cancel out, and I'm left with, it looks like, pi over 3i. So I just took a root. The only thing I'm going to have to do at the end is put this back into rectangular form. Or I'm going to take 2 to the 1/2 and e to the, let's see, does anything cancel out? I've got a 4 and a 2. The 2 goes into 4 twice, so it looks like I end up with -2 pi over 3i as my other root. And again, that is my answer. The last thing that I'm going to do is put this back into x plus yi form. And if you remember, x is equal to r cosine theta and y is equal to r sine of theta. So my answers are going to be, let's see here, square root of 2, 2 to the 1/2 is the same thing as the square root of 2, times the cosine of my theta, which is pi over 3, plus the square root of 2 times the sine of pi over 3 with an I hooked on. Same answer on the other one, only instead of using pi over 3, I am going to use -2 pi over 3. And I'm going to try and squeeze this in. All right, there it is. I did it. And let's see, what is the cosine of pi over 3? The cosine of pi over 3 is 1/2. So I'm going to get the square root of 2 times 1/2 plus the square root of 2. What is the sine of pi over 3? That is root 3 over 2 with an I. So root 2 over 2 plus root 6 over 2i is one of my answers. The other answer is going to be, what is the cosine of negative 2 pi over 3? Think about that for a second. Pause the video if you need to. The answer to that is negative 1/2. And what is the sine of negative 2 pi over 3? The answer to that is negative root 3 over 2. And so when I multiply this all out, I get, and by the way, this square root of 2, that looks like a negative, but it's just a square root of 2. I get negative square root of 2 over 2 minus square root of 6 over 2i. Now I can come up with decimal approximations to this if I want, depending on what kind of calculator you have. Yours is either going to give you exact answers, or it's going to give you approximate answers. But these answers are, it appears, just 180 degrees apart from one another. And we'll take a look at a GeoGebra applet to try and have this make some sense. But it looks like that's my final answer. Now, one thing that you should be asking yourself is, okay, well, these are the two square roots, but what is the principal root? Now, here's what I mean by that. The principal root of, let's just say 4, we know that the square root of 4 is plus or minus 2, but our calculator doesn't give us both of those. And that's because, I'm going to move up to the top here for a second, if we have this radical symbol, that radical symbol means the principal or the primary root, and that answer is 2. If I say what is the square root, like I did on example 6 of 4, that's when you get the plus or minus answer. So we know that the primary or the principal root of 4 is positive 2. What is the primary or the principal root of negative 1 plus I times the square root of 3? Let me clear my screen for just 1 second, because down at the bottom, I tell you the answer to that. The principal square root of a complex number is the one found by using an angle in the interval from negative pi to pi. Now, if you remember at the very beginning of this one, and you'll have to go back and look at the what I wrote before in this video, I had a theta of 2 pi over 3. I also had a theta of negative 4 pi over 3. Which one of these is between negative pi and positive pi? And the answer is 2 pi over 3. So whatever answer came from using 2 pi over 3, that is my principal root. Now this question I know didn't ask that, but in the event you get ones that do, we would say that the principal root, or I could just go ahead and use the radical, the principal root of negative 1 plus I times the square root of 3 is going to equal the one that used the angle of 2 pi over 3, which I believe was the square root of 2 over 2 plus the square root of 6 over 2i. And this is also the one that your calculator gives. Your calculator doesn't give them both. Your calculator is going to only give you the principal or the primary root. One more example for us to look at. This one wants the cubed root of negative 4 root 2 minus 4 root 2i. Now, make a note here that because we have that radical symbol for the cubed root, we are not looking for all three of the roots. We are simply looking for the principal or the primary root. In other words, we need to make sure on this one that our theta is between negative pi and pi, with a parenthesis on the negative pi and a bracket on the pi. All right, the other thing I'm going to do is, because I know that because of the period of these functions, possibly we could see them occur in different quadrants, but negative 4 root 2 and negative 4 root 2, a negative, if I think about where this complex number is, what quadrant do I need to make sure my theta's in? If I go negative and negative, it looks like I'm going to end up in quadrant 3. Negative and negative. Okay, so I have to make sure that my angle not only is between negative pi and pi, but it's also in quadrant 3. All right, so here's what I know. I know that my x value is negative 4 root 2. I know that my y value is negative 4 root 2. And so r squared is going to equal x squared plus y squared. And let's see, what is negative 4 root 2 squared? Well, it's negative 4 times negative 4, which is 16, times root 2, which is 2. And get that twice. So 32 plus 32, I get the square root of 64. So taking the square root of that, I get a radius of 8. That's a nice number. Now I need to find theta. And I can either say that the tangent of theta is equal to my y over my x value. So negative 4 root 2 over negative 4 root 2. I think I'm going to do that one because tangent theta equals 1 is pretty nice. But if I do inverse tangent of 1 in my calculator, I think that I get pi over 4. The problem with this is that pi over 4 is in the first quadrant. It's not in the third quadrant. So we have to remember the period of the tangent function, which is pi, or 180 degrees. So instead of using pi, instead of using pi over 4, I might add pi to it. And if I do that, I get 5 pi over 4. Now, there's a problem with that. 5 pi over 4 is bigger than pi. Pi is 4 pi over 4, so 5 pi over 4 is bigger. So maybe I shouldn't add pi. Maybe I should take away pi. So pi over 4, take away 4 pi over 4, gets me negative 3 pi over 4. And negative 3 pi over 4 is in the third quadrant. So that's what I'm going to use. So now I have my r and I have my theta. So I'm looking for the cubed root of r times e to the I theta. And so I'm going to say that my r value is 8 and my theta is negative 3 pi over 4. Now, another way of writing that cubed root is simply to take that whole thing to the 1/3 power. Now, in this particular case, I think it might be easier actually to find out what is the cubed root of 8 and then multiply that by the cubed root of e to the negative 3 pi over 4. The cubed root of 8 is 2. That's nice. And then e to the negative 3 pi over 4, the 3's are going to cancel, and I'm left with negative pi over 4i. And I think I forgot my I again. I keep doing that. So that's my answer. That is the cubed root of the original complex number. The only thing that we need to do to make this look a little bit better is to take that polar form and to put it back into rectangular form. So I'm going to say 2 times the cosine of negative pi over 4 plus 2 times the sine of negative pi over 4i. Let me just draw a little border here. That's going to give me, let's see, what is the cosine of negative pi over 4? It's root 2 over 2 plus the sine of negative pi over 4 is negative root 2 over 2. Don't forget your I hooked on. And so a bunch of 2's are going to cancel. I'm left with a final answer of the square root of 2 minus the square root of 2i. And your calculator should give you the same thing.